Welcome everyone. My name is Rohit Puri. I'm a network engineer at Meta. And today Hany and I are excited to share our story behind Meta's network evolution, one of the world's most advanced infrastructure to power generative AI. Let's talk about the motivation. Our driving goal has been to design, build, and operate a network which is capable of sustaining and empowering the exponential growth of AI, supporting not only our current AI requirements, but our long-term vision for AGI and for superintelligence as defined by our leadership. As shown in the chart, we have built an interconnected GPU scale cluster that is 100 times larger since 2023. Hany and I will also offer you a preview of the challenges that lie ahead of us as we go beyond 100K cluster in 2026. With this motivation in our mind, let's take a look at the basic network building block that supports our AI infra, the AI zone. As you can see, AI zone is basically a two-stage clause topology where the GPUs or the hosts connect through an RTSW and RTSWs connect to spines through an undersubscribed links. The undersubscription has been done intentionally so that we can actually absorb any failures along the way during our production. The AI zone occupies part of a data center building, and there could be multiple AI zones which can get into one data center building. Let's take a closer look at the structure of type 1 data center, which is a basic building that is deployed at Meta. As you can see, in a Meta DC type 1, we have 4 data halls, and each data hall can actually take up to 2 AI zones, which means we can actually squeeze in 8 AI zones into a given data center type 1 building. There are MDFs, which are the first level of network aggregation point for server racks. And then there is BDFs, where we put all the core of the DC fabric. Now with this brief introduction about Meta's data center layout and the AI zone building block, let's take a look at the main agenda for our talk today. We will be delving into details of the network architecture deployment for our Gen AI. Thereafter, we'll go over all the challenges that we ran into when we were doing the 100K cluster turnup and the lessons that we learned along the way. And finally, we'll conclude with the next steps in our journey. With this, I will now hand it over to Hany for a deep dive into network builds we have developed at Meta to support these generative AI services.
Thanks, Rohit. Hi, everyone. I'm Hany Morsy, a network engineer at Meta. Let's keep in mind some keywords from Rohit's introduction, like the AI zone, RTSW, CTSW, data hall, BDF, etc., as we will refer to these keywords throughout the presentation. Let's dive in. Here is a 24K cluster. Our journey with Gen AI deployments at Meta started with this 24K cluster. This network was built in 2023 specifically for Llama 3 training. As we see in the drawing on the right, the network occupies one single data center building of type 1 with 4 data halls. We removed all non-AI servers from the DC and deployed 2 AI zones per data hall. This CRAM approach helped us maximize the GPU scale within a single building. All right, so now we have 8 AI zones in this building. We need to connect them together. For that purpose, we installed a super spine layer that we refer to as the RTSW layer, or the aggregation training switch layer. This aggregation tier resulted in 24,000 interconnected GPUs in that one single building. While this 24K cluster served its purpose for Llama 3, next-gen AI models were more complex and demanded even greater GPU scale. Now, this brings us to the 100K cluster. This is the 100K cluster, and the first thing we notice is that the 100K cluster is multi-building. This is one important takeaway from the evolution of our Gen AI infrastructure, the transition from one building to multi-building. The network was built in a type 1 region comprising 5 buildings. Again here, each one of these buildings houses 4 data halls, so now we have a total of 20 data halls across the 100K region. Similar to the 24K cluster, we cram 2 AI zones per data hall. As we see in the drawing, buildings 2, 3, 4, and 5 are fully populated with 8 AI zones each. Building 1, however, has only 6 AI zones, with 1 data hall dedicated to support and services. Example of support and services would include storage servers that feed the dataset to the GPUs. So in total here, we have 38 AI zones in this region. Each AI zone supports approximately 3.4K GPUs, leading to a staggering total of 129K GPUs across the entire region. This makes it one of the largest AI clusters in the world. Let's take a deeper look at the network topology per building. Here we see our 4 data halls and 2 AI zones per data hall. Each AI zone is exactly what Rohit showed us earlier, a 2-stage claw topology with RTSWs connected to the GPUs and aggregated by a set of CTSWs. We have 8 AI zones in the building interconnected by 76 ATSWs. Each and every CTSW in the data center uplinks to all 76 ATSWs. The ATSW layer not only interconnects the 8 AI zones within the building, but also connects the building to other buildings in the region, providing regional connectivity. It's also worth mentioning here that for one AI zone to cross the ATSW layer and talk to another AI zone, there will be oversubscription of roughly 3 to 1. All right, now we take a closer look at the regional connectivity. The regional network is constructed by fully meshing the ATSWs that share the same index from all 5 buildings. For example, ATSW1s from all 5 buildings are connected together in a full mesh. All ATSW2s are connected in a full mesh, and so on, all the way to ATSW76s. This basically creates 76 distinct orthogonal planes depicted here in the drawing with the purple rectangles. Within each one of these planes, the ATSW uses 144 uplinks that are evenly distributed with 36 uplinks to each of the other 4 remote ATSWs in the region. It's also worth mentioning here that the fiber infrastructure between buildings is based on OSP, or what we call the outside plant fibers. End-to-end physical distances between a pair of GPUs that are farthest away from each other may reach 3 kilometers. But now let's take a close look at how we used this massive 129K infrastructure to support generative AI training. All right, the first thing we note here is that this 129K cluster was used to train and deliver Llama 4 earlier this year. The largest workload used to train our production Llama 4 model included 32K GPUs. Soon after that, we wanted to push the boundary with even larger training workloads. So we placed roughly 100K GPUs in the same job simultaneously. That 100K job is some of the largest training workloads at Meta and perhaps ranks very high in the world as well. This was important to give us confidence that our infrastructure is capable of handling the most demanding AI tasks. So in the drawing on the top here, we see a rough concept of the GPU chunks that make up the 100K capacity distributed across the 5 buildings, with a small amount of GPU buffer to help keep the job going in case of failures. The drawing at the bottom shows the estimate latency between different pairs of GPUs in the region in units of microseconds. In this massive and distributed workload, training throughput becomes a challenge. To improve performance, we invested in 2 things. 1, optimizing the communication library for cross-building traffic. And 2, we combined different types of parallelisms in the workload. Now we return back to Rohit to talk about the challenges that we experienced while bringing up this 129K cluster.
Thank you, Hany. This is really a very good design. But We still anticipated challenges when Gen AI workloads start to ramp up on this fabric. So we took some proactive steps to address these challenges. We knew network congestion is going to be a challenge. This is a large-scale GPU intercommunication, and with the traffic being bursty, we expected a lot of traffic at the spine and superspine layers. There is a risk of queue buildups, high tail latencies, and we also rely a lot on PFCs. All of this risked triggering HOL blocking kind of thing, which can kill the throughput and hurt the jobs. So we deployed deep buffer switches at spine layer to absorb this congestion. We also adjusted our buffer thresholds in RTSW to such a high amount so that we could minimize the PFCs that they would actually exert towards the spines and towards the rest of the network. The another issue we ran into was the long distance. Now, we all knew from Hany's discussion that DCs span over 5 buildings. There is a 3 kilometer distance covering all of these DCs. We can't do much about this physical distance, but we did deploy low latency optimized versions of the CTSWs. The idea has been to lessen the impact of some of these queue buildups and be able to run and absorb some of those error problems better. We also targeted this with a very specific use case for our deployments. Now, we did not anticipate GenAI training to progress without challenges. We needed the ability to isolate, debug, and resolve production issues quickly. So we invested heavily in the dashboards and extensive monitoring across all layers of the network. In our dashboards, we actually had tabs for every layer where we could actually figure out what exactly is going on, what are our outliers and how they are behaving, and which ones are the bad ones, so that we could quickly isolate the problem. Now the issues did happen. I will be taking you through some of the interesting issues we ran into during this course of our turnup. So one of the early issues was very high congestion drops at RTSW layers. Now, we would expect that a lossy queue would drop traffic, but we did not expect that a queue which is actually taking less than 1% of the traffic would drop. However, because these are lossy traffic queues, they will drop the traffic. Now, in our case, we were actually carrying some of the controlled rocky traffic onto these queues, and it was also carrying the monitoring traffic. And when these packets got dropped, it actually impacted the job performance. So we figured we had to actually move all our rocky traffic, control traffic, back into the lossless queues. And we readjusted the buffers in such a way so that the probability of drops on the lossy queues actually goes down quite a bit. Once we rolled out this fix, we were able to move forward. We had hardly moved forward when we hit a second issue. And this time it was at the spine layers. Again, it was triggered by a very high rate of traffic and congestion. We had a high amount of concurrent traffic ingressing from the RTSWs to the spine layers. And at the same time, we had a concurrent amount of PFCs exerted by RTSWs, who were the receivers, onto these spines. All of this resulted in a transient buffer drops on the CTSWs. We could not recreate the problem in a very clear manner, and that became kind of a challenge for us. But we were able to kind of modify these hardware settings with the help of the vendor to exert PFCs when such a situation happens. And when that did happen, the CTSWs could actually PFC back onto the RTSW and be able to avert the contention issue that we would run into that caused the drops. So we rolled this fix in at the runtime with zero downtime across our 100K fleet. And we were able to roll out and see that we were exerting some of the PFCs from the spines, but not a whole lot. And we were able to get beyond this point and prevent any drops. An interesting issue, a kind of another version of a problem that we ran into was that we actually saw a performance variation across DCs for the same job. As you can see in the graph, one of the DCs actually performed 30% inferior as compared to another DC. Now, this problem could only be seen at 8K GPU scale, which was very hard to procure for debugging. What made this debugging more challenging was that the DC where we saw the regression had a new NIC firmware, and we suspect that new NIC firmware had issues. Once we started debugging, we found there were multiple issues. The first issue was obviously related to the NIC firmware, where there were setting drift from our rest of the DCs. We kind of recognized that these settings changed and we were able to address it quickly. But that only reduced the gap of the regression. It did not solve the regression completely until we actually found the root cause for the remaining regression. And that was caused by our monitoring tooling, which actually was monitoring some of the optics, and it had a CPU contention throttling the throughput on the NICs. Once we fixed that monitoring, we actually were able to reclaim all our performance and we were back on track to delivering the GenAI models. While these were some of the interesting network issues we hit during our 100K cluster training, these were not the only ones. We did mitigate them, fix them, learned our lessons, and kind of moved on to do higher and higher scale jobs. Next, I will hand the presentation over to Hany, who will lead us through the conclusions and outline of what lies ahead for us in 2026.
Coming to the last section in our presentation today. All right, let's capture a few takeaways from our talk today. So for one, GenAI model complexity is constantly escalating. Demand for power and compute resources always on the rise. For two, our network supporting the AI services has evolved. Before generative AI, we used to build standalone AI zones, mapped one-to-one with a data hall. But then we evolved from one data hall to a whole data center building, and that supported the first GenAI model. Then we expanded from one building to an entire region, encompassing 5 buildings and supporting a remarkable scale of 129,000 GPUs. Other takeaway is that new challenges emerged with larger network diameter around latency, oversubscription, and congestion. Let's take a peek into the future. The future promises even larger networks. We may call them gigaclusters that will span entire metropolitan area, connecting multiple sub-regions, possibly through a dedicated regional aggregation layer. The GPU or the accelerator scale may become in the hundreds of thousands, may even cross a million. New challenges will absolutely emerge with that new massive scale. For one, we will need to train models over very long distances, potentially hundreds of kilometers. For two, we will need to train our models across a diverse set of data center types and heterogeneous accelerator models, NIC cards, switching platforms across the sub-regions. We're incredibly excited about what the future holds for us. Thank you so much for listening to our story today.